Okay, in this video we're going to look at the inverse matrix method for solving a system of equations. We'll look at systems of two equations and two unknowns, and one example of a system of three equations and three unknowns using the inverse matrix method. And so probably the easiest way to do this for a 2 by 2 matrix to find the inverse is first to find the determinant. So the determinant of a matrix A, which has entries A, B, C, D, it's going to be multiply AD and then subtract CB or BC. And provided that the determinant's not 0, then the inverse, we'll call a to the minus 1, is going to be 1 over the determinant, so 1 over AD minus BC. And then we'll switch the A and the D along the diagonal, and the B and the C will make opposite signs there. So that is our inverse. Okay. To show that this is in fact the inverse, if we take A and A inverse, A was A, B, C, D. A inverse was 1 over the determinant, and then we switched A and D, and C and B become opposite signs. Okay. And we have a property of matrices that allows us to do the scalar last there. So we'll go ahead and do the matrix multiplication. We'll put the scalar out in front. Okay, so we'll do AB times DC, D negative C, okay. So that'll give us AD minus BC. Oh, it looks like I wrote down, I think I end up fixing it later. This should be a B right here. So I think I end up fixing it later. So this should be a CB or BC there. And then we're going to do AB times negative B and A. So it'll give us negative AB plus AB. So those are going to end up canceling out. CD times DC. So that'll give us CD, and then, oh, did I have a minus sign? I sure did. And then D times negative C will be a negative CD. And then finally CD times negative B and positive A. So it'll give us negative CB plus AD. Now the diagonal, this diagonal here, that's going to drop out because you have the CD and minus CD and then negative AB and positive AB. So those are going to go away. You do have AD minus CB. So here's AD minus CB, and here's another AD minus CB. And so what's going to happen is when we put that scalar in there, we're going to get the identity. So we'll get 1, 0, 0, 1. So that is at least a right-handed inverse. So we'll go ahead and do the same thing on the other side. And we'll check, does A inverse times A equal the identity matrix? Okay, so we have 1 over the determinant, and then there is the A inverse, and then A. And then we'll go ahead and do our matrix multiplication. And then I did correct myself later as I was making the video. I said, oh, oops, I had the wrong thing there. And apparently I wrote the same thing here, so let's go ahead and fix this up. Sometimes we get carried away in the excitement. Alright, so that should be a B there. Alright, so we're going to do D and negative B times A and C, so we get AD minus BC. And so when we distribute this in here, that's going to make a 1. And then we'll do D and negative B times B and positive D, so BD minus BD. Negative C and A times positive A and A. Negative C and A times A and positive C. So that gives us negative AC and then plus AC. And finally, negative C and A times B and D. So that'll give us negative CB and plus AD. So as we distribute, this will be a 1, and this will be a 1. These are going to end up being zeros. Okay. And so we get the identity matrix on the other side also, so that is a little bit of a verification, at least for the 2 by 2, that this is in fact the inverse matrix. Okay, so let's go ahead and look at kind of the setup for a system of equations, how we would solve it using the inverse matrix method. And I think we're going to do that in a minute. I think we're going to practice finding the determinant and the inverse, and then we'll set it up as a system of equations. It's coming up. Okay, so let's say that I have this matrix here, and I will call it matrix A for convenience. The determinant of A will be -1 times 1, and then minus -2 times -3. And so that will give us -7, and our determinant is not 0, so we do have an inverse. So A inverse will be 1 over the determinant. We'll switch the -1 and 1, and the -3 and the -2 will have opposite signs, so they'll both be positive. Okay, and then we'll go ahead and distribute the -1/7 through, and that's our inverse matrix. Okay, let's do another one. We'll look at 2, 13, 5, and 32. So first thing we'll do is we'll call that B for convenience, the determinant of B. It's going to be 2 times 32, which is 64, minus 5 times 13, which is 65. So the determinant is -1. So B inverse will be 1 over the determinant. Switch the 2 and the 32, and then the 5 and 13 will have opposite signs. Distribute that -1 through, and we have our inverse matrix. Okay, so that's finding the inverse matrix and also finding the determinant of a 2 by 2 matrix. Okay, so this is what I was thinking the next slide was. So here is the inverse matrix method for at least a system of 2 equations and 2 unknowns. And it'll be similar for a larger system. Okay, so if we take our system of equations, ax plus by, and we'll say that's equal to k1, and our second equation, cx plus dy, is equal to k2, we can write it as this system of equations, and I'll go ahead and give us a little bit more justification. So this is a 2 by 2, and this is a 2 by 1. And so that product is defined, and so if we multiply them, we'll do AB times XY, so that'll be AX plus BY for our row 1, column 1, and then our row 2, column 1 will be CD times the XY, so that'll give us CX and DY, and that'll be equal to K1 and K2. And so 2 matrices are equal to each other if they have the same size, which these do, and so then the corresponding parts are going to be the same. So we have AX plus BY is equal to K1, and CX plus DY is equal to K2, so this is a good representation there. Okay, so we can represent the system of equations like this. And so let's go through and kind of go through the shortcut for doing the inverse matrix method. So we don't set this up every time. So we're going to call the coefficient matrix that first matrix, which is the A, and that'll be A, B, C, and D. B is going to be the consonants equal to on the other side. X will be the X and Y. And so what we're going to do is we'll write this same equation with matrices, so it's AX is equal to B. And as long as we can find the inverse, so we did practice how to find the inverse matrix, as long as the inverse matrix exists, what we're going to do is we're going to multiply both sides of that equation, and it has to be on the left side. Remember, matrix multiplication is not, in general, is not commutative. So we're going to multiply the left side by A inverse. So A inverse times AX is equal to A inverse B, and A inverse and A are going to give us the identity I times X, and that's going to be equal to A inverse B. When we did do the matrix multiplication in the past, we did do something like the identity for 2 by 2s times a 2 by 1 matrix. And what happened was we got the 2 by 1 matrix back, so there'll be x is equal to A inverse B. And so when we're solving by the inverse matrix method, what we're going to do is we're going to figure out our coefficient matrix, figure out our matrix B, and then we're going to find A inverse. And then to solve by the inverse matrix method, you'll simply multiply A inverse and B. And so let's go ahead and try that out. So we're going to solve using the inverse matrix method. Negative x minus y equals 8, not 8, negative 80. 8x plus 5y is equal to 77. So we're going to identify our coefficient matrix, which is negative 1, 8, and 5. So the coefficients off the x and y's. We're going to go ahead and identify x, it's xy, and the b, which is negative 80 and 770. The determinant of a will be equal to negative, so it'll be 5 times negative 1, which will be negative 5, and then minus negative 1 times 8. So our determinant is going to be 3. So our inverse matrix will switch the negative 1 and 5 on the diagonal, and then make the 8 and the negative 1 on the other diagonal opposite sides. And of course we have the multiply by 1 over the determinant on the outside there. And so there is our inverse matrix: 5/3, 1/3, negative 8/3, and negative 1/3. And so if we're doing the inverse matrix method, we need to know A inverse and we need to know B. We got all that. So x is equal to A inverse B. So we just found A inverse. So 5/3, negative 8/3, 1/3, and minus 1/3. B is negative 80 and 770. This is a valid multiplication. So 5/3 times negative 80 and 1/3 times 770. So it'll be negative 400 over 3 and 770 over 3. And then negative 8/3 times negative 80 will be 640 thirds. And then negative 1/3 times 770 will be negative 770 over 3. Okay, so we have a common denominator, and so we'll go ahead and simplify that down. So that'll be or combine our like terms. So we have 370 over 3, and negative 130 over 3, and that'll reduce to. Well, I guess it doesn't reduce. No, we don't reduce. We didn't have any common factors. Okay, so there is our solution. Not the nicest looking thing, but it's 370 over 3, comma, negative 130 over 3. So let's go ahead and look at another example of this. And maybe this time let's see. We got 6x minus 7y is equal to negative 731. Negative 3x minus 3y is equal to 315. Identifier A is the coefficient matrix. We'll mention what matrix X is and what matrix B is. So we'll go find the determinant. So 6 times negative 3 minus negative 3 times negative 7. So we get negative 18 and minus 21. So we get negative 39 as our determinant. So that's not 0. So we do have an inverse matrix. So A inverse will be 1 over negative 39. And then we'll switch the 6 and negative 3. And then the negative 3 and the 7 on the other diagonal. They're both negative, pardon me. So the 3 and the 7 will become positive now. Okay, we'll go ahead and distribute. And so we get 3 over 39, negative 7 over 39, negative 3 over 39, and negative 6 over 39. Now we could reduce all of this, but I'm going to leave that alone because we'll end up needing that common denominator of 39, so that'll make it a little bit easier for us. So we won't reduce there. We'll reduce at the very end if we can. Okay, so inverse matrix method, A inverse B. So here is A inverse. And here's B. Okay, so we'll do row 1 times column 1, so 3 times negative 731 will be negative 2,193 all over 39. And then negative 7 over 39 times 315 will be negative 2205 over 39. And then we'll do row 2 times column 1, so negative 3 times negative 731 will be 2,193 over 39. And then the negative 6 over 39 times 315 will be negative 1,890 over 3. So here's why I didn't want to reduce. So now we have common denominators, so we can go ahead and just go ahead and add those numerators. And so we get negative 4,398 over 39 and 303 over 39. And I believe we can do a little bit of reducing. So we can reduce by 3, and we get negative 1,466 over 13, and 101 over 13. And as an ordered pair, that'd be 1,466, negative, and it was negative over 13, and then 101 over 3. Okay, over 13. Pardon me. So again, not the nicest numbers, but if we keep that common denominator, it does make things a little bit easier. So I think we're going to look at an application or two, and then we'll look at what happens if we try to do inverse matrix method with a larger matrix. So here we're going to do an application, and it says a man flies a small airplane from Fargo to Bismarck, North Dakota, and it's a distance of 180 miles. Because he's flying into a headwind, the trip takes him 2 hours. On the way back, so I guess that's the trip going. So on the way back, the wind is still blowing at the same speed, so the return trip only takes 1 hour and 12 minutes. What is the speed in still air, and how much is the wind? What's the speed of the wind, I guess? And so we'll make the assumption that we're going to be flying at the same speed, the plane speed at least, and then the wind's going to be the same. So that's going to be the uniform motion, which is distance is equal to rate times time. And if we're going from Fargo to Bismarck, we have 180 is the distance, and then we can say that x is the speed of the plane, and y is the wind. So we had the headwind, so the x minus y is the speed of the plane minus the speed of the wind, and then times the time of 2 hours. And then from Bismarck to Fargo, again, it was 180 miles. But this time, the wind is going to be pushing the plane, so we can add the two speeds. So x is the speed of the plane, y is the speed of the wind. And then we have a little bit of a units issue because we have 12 minutes and 1 hour. So if we're doing x and y is the speed of the plane and the speed of the wind, I think we're going to make the assumption that we're in miles per hour. So we do need to convert the 12 minutes into hours. So it's 1 hour to 60 minutes, and so we'll do the unit conversion, and so 12 minutes is 1/5 of an hour. So if we have 1 hour and 1/5 of an hour, that's going to be 6/5 of an hour, or 1.2. So we get a nice decimal, so we can use the nice decimal, okay? So we get 1.2. All right, so then if we distribute the 2, it'll have 2x minus 2y is equal to 180. And distribute the 1.2, 1.2x plus 1.2y is equal to 180. So then we can set up our coefficient matrix as 2 minus 2, 1.2, 1.2. We'll find the determinant of that matrix. So that'll be 2 times 1.2 minus negative 2 times 1.2, and that'll be 4.8. Then we can find the inverse matrix, so it's 1 over 4.8. switch the 1.2 and 2 on the main diagonal, and then the 1.2 and the negative 2 on the other diagonal here, they will have opposite signs there. And then distribute that 4.8 through, and I'm going to go ahead and leave it as the 4.8 in the denominator. I don't know if I'm going to have real messy decimals or not, so we'll leave it like this so that I do have a common denominator, and then we'll worry about reducing later. Okay, so inverse matrix method, x is equal to A inverse B. Okay, so A inverse we found. We'll have to go get B. So B is the two numbers that we're equal to for the, and that's going to be 180 and 180. Okay, so we got our B, 180 and 180. Okay, so we're going to do row 1, column 1, so we'll do that multiplication. So 216 over 4.8 plus 360 over 4.8. And then after I simplify that down, that's going to give me 120. So that is the speed of the plane is 120. And then we'll do row 2 times column 1. So negative 216 over 4.8, and then plus 360 over 4.8. And so after doing those calculations, the wind speed is going to be 30 miles per hour. So there is our plane speed and our wind speed. Okay, so I think we got 1 or 2 more examples. I can't remember of applications planned here. So let's see what we have on the next page here. All right, so what do we got? Okay, so let's stop it from doing anything. Okay, so it says the admission fee at an amusement park is $1.50 for children and $4 for adults. On a certain day, 310 people enter the park, and the admission fees collected totaled $790. How many children and how many adults were admitted? So that's what they're asking us, is for children and adults. So we can say X is the number of children, Y is the number of adults. And so we'll need to get 2 equations. So if we add the number of children plus the number of adults, that was the total number of admissions, which is 310. And then if we want to find the revenue, $1.50 times the number of children plus $4 times the number of adults was equal to 790. Okay, so we can go ahead and get our matrix A, which is 1, 1, 1.5, and 4. And we can also mention our matrix B, which is 310 and 790. We'll find the determinant of A, which will be 1 times 4 minus 1 times 1.5. So it'll be 2.5. A inverse will be 1 over the determinant. Switch the 1 and 4. Make the 1.5 and the other one negative, opposite signs. And then we'll go ahead and multiply that 2.5 through. So this one ended up being a little bit nicer decimal. So 4 divided by 2.5 was 1.6. Negative 1 divided by 2.5 was negative 0.4. Negative 1.5 divided by 2.5 was negative 0.6. And then 1 divided by 2.5 was 0.4. So we ended up, I don't really want to deal with repeating decimals. It gets too messy. So, but in this case, we got nice decimals. Okay, so then we're going to do inverse matrix method. So X is equal to A inverse B. So A inverse is 1.6, negative 0.4, negative 0.6, and 0.4. And matrix B, 310 and 790. So we'll do row 1 times column 1. So 1.6 times 310 is 496. Negative 0.4 times 790 is negative 316, and that'll give us 180, so that's the number of children that attended the amusement park. And then we'll do row 2, column 1. So negative 0.6 times 310 will be negative 186 plus 0.4 times 790 will be positive 316. And so that'll be 130, so that's the number of adults there. Okay, and so that is inverse matrix method again, using to solve a nice system of two equations and two unknowns. This time it happened to be an application. Okay, so I think this is where we get into the inverse of a 3x3 matrix. So the process is a lot more involved. So on the left-hand side there, that's the matrix that we would like to find the inverse of, and we're going to augment it with the identity of the appropriate size, and this size would be 3x3. So here's the identity matrix. Okay, and we could do this strategy also, or this method, for systems of two equations and two unknowns. This would work, but the determinant way is probably a little bit quicker. Okay, and so what we're going to do is we want to change this side to look like this, and to do that we're going to do something called Gauss-Jordan elimination. And it's very similar to Gaussian elimination, but Gaussian elimination makes a 1s here and 0s down here, and we don't care about what's going on in the upper part of the matrix. So Gauss-Jordan makes the top part 0. So it's a little bit more involved than regular Gaussian elimination. Okay, and so we'll draw kind of a diagram of what the pattern is for doing the Gauss-Jordan elimination here for the 3x3. Okay, so first thing we'll do is we'll make a 1 in the upper left-hand corner, and then we'll make everything else 0s. So that's the same thing as Gaussian elimination. Then we'll make a 1 in row 2, column 2. So that's the same as Gaussian elimination. The thing that's going to be different is we're going to make a 0 up here. We already do a 0 down here by Gaussian elimination, but we're just going to do an extra 0 here. So 0 up here and a 0 down here. And then it will be like Gaussian elimination. We'll make the bottom right be a 1, and then the other two new things would be to make a 0 here and a 0 here. And you're going to make zeros pretty much the same way that you did with regular Gaussian elimination. Okay. So doing this with a 3x3 is more time consuming. So we'll do one example of that and see what we got. See what the process looks like. Okay, so here is our big old system of equations. So we're going to solve 3x minus 8y plus z equals negative 16, minus x plus y minus z equals 0. X minus 3y is equal to negative 7. So what we're going to do first is we're going to put in our coefficient matrix. So doing the x's, that would be 3, negative 1, and 1. The y's will be negative 8, 1, and minus 3. And the z's, there's no z on the last equation, so we'll have a 0, a negative 1, and a 1. Okay. Then we're going to augment that with the identity matrix for 3x3s. So there it is. Okay, and then we'll write down the pattern that we would like to do. Okay. All right, so first thing we'd like to do is make this a 1 here. And one way we could do that is we can divide the top row by 3, but then we'd have a bunch of fractions floating around. So probably the best thing to do is, you already got a 1 here, so let's move it up to the top. So we're going to do a row swap between row 1 and row 3. So row swap between row 1 and row 3. Row 2 is still row 2. Okay. So we've got the 1 up there. The next thing we'd like to do is we'd like to make both of these zeros, so that's the same as Gaussian elimination. So we're going to do row 1 plus row 2 to replace row 2. So row 1, we'll write it out. And there's row 2, and then we'll go ahead and add them. So So we get 0, minus 2, minus 1, 0, 1, and 1. Okay, so there's your new row 2. And then we're going to make a 0 here. This is in column 1, so we're going to use row 1. And the opposite of 3 is negative 3. So negative 3 row 1 plus row 3 replaces row 3. So negative 3 row 1 is going to be negative 3, 9, 0, 0, 0, negative 3. Row 3. And then our new row 3, 0, 1, 1, 1, 0, minus 3. So there is your new row 3. And row 1 was unaffected. Okay, so we did use row 1 to make zeros in column 1, but we didn't change it. Okay, so we are, I guess, a third of the way there. We'll see what else we can do. Okay, so we'll clean this up because we need a lot of paper or board space to do this. Okay, so the next thing we'd like to do is we'd like to make a 1 there. And we already got the 1 here, so we don't want to do a row swap with row 1 because then that would move it down here or here. We don't want to do that. So I have two choices. I can divide the middle row by negative 2, but then I'd have some fractions. Or we can do a row swap. So we're going to go ahead and do a row swap here. So we're going to swap rows 2 and 3 to get the desired 1. Okay, so perform our row swap. So switch rows 2 and 3. So row 1 is unaffected here. Okay, so now we have the 1 there. So we would like to make a 0 here and here. They are in column 2, so we want to use row 2. The opposite of negative 3 is positive 3, so we'll do positive 3, row 2 plus row 1, replace row 1. So 3 row 2 will be 0, 3, 3, 3, 0, minus 9. And row 1, there it is. We'll go ahead and add those to make our new row 1. So we get 1, 0, 3, 3, 0, and minus, it should be a minus 8. There we go, minus 8. Okay. 1, 0, 3, 3, 0, and minus 8. Okay. Now we'd like to make a 0 here. That is in column 2, so we'll use row 2. Okay, the opposite of negative 2 is positive 2, so we'll do 2 row 2 plus row 3, and that'll replace row 3. So 2 row 2 will be 0, 2, 2, 2, 0, minus 6. Row 3, and your new row 3 will be 0, 0, 1, 2, 1, and negative 5. Okay, and so we took care of the second column. We also got a 1 here for free, so lucky us, we get one less step to do here. Okay, and so we did use row 2, but we didn't change row 2, so row 2 is the same there. Okay, so the last thing we need to do is we need to make a 0 here and here. They are in column 3, so we're going to use row 3. So we'll do negative 3 row 3 add to row 1 to replace row 1, and negative 1 row 3 add to row 2 to replace row 2. So those are the last two things we need to do here. So we'll go ahead and write down the same matrix again. And we'll perform those two operations there. So negative 3 row 3 plus row 1 to replace row 1. So negative 3 row 3 will be 0, 0, negative 3, negative 6, negative 3, and 15. And then we'll write in row 1. And then we'll go ahead and add for our new row 1. So 1, 0, 0, minus 3, and that should be a 7. Okay. Okay. And the other row operation we needed to do was negative row 3 plus row 2 to replace row 2. So negative row 3 will be 0, 0, minus 1, minus 2, minus 1, and 5. Row 2, and we're going to add them and get our new row 2, which is 0, 1, 0, minus 1, minus 1, and negative 2. Positive 2, pardon me. Alright, so there it is. And we did use row 3, but it is unaffected. Okay, so now we've changed the left-hand side to look like the original right-hand side. So the negative 3, 7, minus 1, 2, 2, 1, minus 5, that is now your inverse. So x is equal to A inverse B. So A inverse was minus 3, 7, negative 1, negative 1, negative 2. Oh, it was positive 2, wasn't it? Let's double check. Yes, positive 2. Okay. And then minus 5 there. B is, if we went back to the previous slide there, was the coefficients minus 16, 0, and a negative 7. Okay. So, oops, we went too far. Rewind a little bit. Okay, so negative 16, 0, and minus 7, that was your B. Okay, so we have a 3. Well, we can't draw with that one very well. We have a 3 by 3 and a 3 by 1, so that matrix multiplication is valid, and we'll have a 3 by 1 as our answer. Alright, so row 1, column 1. So negative 3 times negative 16 is 48. Negative 3 times 0 is 0, and 7 times negative 7 will be negative 49. Okay, so the result there would be negative 1. Row 2, column 1, negative 1 times negative 16, 16. Negative 1 times 0, 0. And 2 times negative 7 will be negative 14. So then we get 2. And then finally, a row 3, column 1. 2 times negative 16 is negative 32. 1 times 0 is 0. And negative 5 times negative 7 is positive 35. And so that gives us 3. And so our ordered triplet is minus 1, 2, and 3. Okay, so it is quite a bit more involved finding the inverse for a 3 by 3. But if you have a good handle of Gaussian elimination, then doing the Gauss-Jordan elimination isn't too much more of a stretch there. Okay, last thing we're going to go ahead and take a look at is what happens if the determinant is 0 for like the 2 by 2. So then just some comments at the end here. And we had these ones, these, I think they're the same ones in the previous video where we were doing, I think, Gaussian elimination and what happened here. So here's my matrix A. It's 2 minus 3, 6 minus 9. And when I find the determinant of that, it's going to be negative 18 minus negative 18. So that's going to be 0. And so I think this one we had, this one is going to be an infinite solutions. Is that right? Is that yeah, that was an infinite solutions problem. So if your determinant is 0, it could possibly be infinite solutions. If we make a minor adjustment to the problem, so we just change the coefficients is equal to, so 12 and 10, yeah, this is the same problems we had before. It's going to have the same determinant, and so I am saying it was infinite solutions again. Okay, so let's erase the extra infinite solutions here. Okay, so you can solve. You'll have to solve it by a different method to get the infinite solutions, and then the problem number 46 has no solution. So if your determinant is 0 for solving a system of 2 equations, 2 unknowns, there could be a no solution or an infinite solution. So your best bet is to either solve it by Gaussian elimination or the regular elimination or substitution methods from previous videos that we did there. So that is quite enough for this video. So we'll see you next time.